Right now, what we are going to do is discuss some of the features regarding the metamorphic facies as per uh, on a basic skill. As a revision also, some of the things which we have done in the class regarding the processes that a rock or a mineralogical assemblage undergoes due to the changes in the pressure and temperature as well as activity of the components and fluids during metamorphism. The approaches those could be made are quite now. The reason is that whenever you see a region, you are observing it in terms of a pressure, temperature, field, as this axis is pressure and this axis is of temperature. And what we have known from the thermodynamical viewpoint, that during the increment of pressure temperature, the phases which are consisting of the components in Gibbs free energy field, they will change depending upon the minimization of the Gibbs free energy in certain fields or domains, and as a result there will be some mineralogical changes associated mostly with the pressure and temperature. And as we have known that if we draw it in terms of the geothermal gradient, if it is depth and it is temperature, there will be types of geotherms, as well as there should be solidus and liquidus lines with increasing temperature as well as increasing depth. Now the thing is that whenever we are trying to access these different mineralogical assemblages, like some of the mineralogical assemblages we will see here, some of the mineralogical assemblages we will see here, some of the assemblages which will be residing here, some of them will be here, and some of the assemblages we will see here, and some of the assemblages we will see here. Depending upon the separate regions or factors as well as the bulk composition of the whole system involved, the transformations of the minerals take place. While these transformations are taking place, you will be able to observe some of the interesting outcomes in this regard, like change of biotite, quartz, plage, assemblage to garnet, potash feldspar and fluid. Now in classic metamorphism, the fluid should persist in the system, but mostly the higher grades produce so much of melt that we discussed when the LPT is reached. Some of the melt can escape the system. Metasomatizing others. Now this is a big thing, that during the changes or during the processes of metamorphism, some of the fluids might escape in the system. However, some of the bulk, some of the compositions will remain in the system as metatexitic texture with paleosome, mesosome, melanosome, leucosome, etc. And as we have discussed in pegmatites, that they develop different kinds of structures in the field, like nebulitic structure and etc., depending upon the melt and its behavior. Now the paleosomes, actually these are actually outcomes, that is melanosome and leucosomes are outcomes of a high grade of metamorphism generated from a paleosome which was present as an earlier assemblage of phases in the rock. Now obviously we can see that there is a role of mineralogical assemblage that can help us identify the situation where a rock or mineralogical assemblage had been or been going through. Now the reasonings, as well as the different types of things that we are going to understand, as well as these different types of textures that we will see, are different ensembles of minerals, and these set of minerals will be known as facies. Now what I am telling is that changes in pressure, temperature and set of mineralogical composition as an outcome of that pressure, temperature reached by the rock due to the energy minimization and their appearance in a stability field for a bulk. So there should be a dependency of the bulk, whichever the mineral is generated during the energy minimization in an assemblage due to changes in pressure and temperature. This whole concept can be known as facies. Okay. As an example, we have seen it here that this is an example of a prograde metamorphism. However, in case of retrograde metamorphism also, garnet can transform to plage pyroxene. As an example, plagioclase and pyroxene can transform to garnet. Depending upon the way the retrograde metamorphism or rather the post-peak metamorphism is taking place. These mineralogical assemblages are typical for mafic rocks that you should know. Obviously, there is a role of bulk that I have told you. Now, in case of the mafic rocks, the concentration of the aluminium in a particular bulk is not that high, which is very evident or prudent in case of a pelitic bulk, where some of the sediments like kaolinitic clay, montmorillonitic clay, they undergo degrees of metamorphism, generating minerals like barite and muscovite, or even muscovite can be converted to different sets of minerals, and slowly some of the aluminium rich mineral phases, they come into existence. The most important sets of minerals that we might find in a pelitic metamorphism are aluminous, sillimanite, or even kyanite, which are in low grade are andalusitic in composition. Now, kyanite and sillimanite, they are both polymorphs of Al2SiO5. Kyanite is a typical resultant when a pelitic rock get metamorphosed in a high pressure, in an ultra high pressure or high pressure situation. Okay, but this kyanite or even sillimanite should not be found in case of a metamorphism of a strictly mafic bulk. So, as well as there is a mineral which is known as cordierite. Cordierite, it is nothing but hydrous magnesium silicate, and which bears aluminium in its structure, or rather if I try to search the composition of cordierite, this is a magnesium iron aluminum bearing silicate. It's a solid solution, and like this each and every minerals those are, or I am going to discuss about, or you are going to find in a pelitic system has their own set of mineralogy as well as the association of the elements in different sites of minerals is also very, very important in character. So it's a very important thing that you should get an idea, as well as you should be very much akin to know the mineralogical compositions of these individual mineral phases, as well as the structures or the atomic sites where ions like sodium, calcium or potassium should go, sites where magnesium, iron, titanium should go, where ferric should go, because depending upon the geochemistry or geochemical perspective, we have known that there is a role of charge and ionic radius as well as coordination number, where these elements can take their places in individual phases of the minerals. Aluminium can go both in octahedral as well as tetrahedral site depending upon pressure, temperature and various sets of minerals, and this can be sometimes good or handy in analyzing the pressure from a mineral, like in case of an amphibole. Now, amphibole, it's very preponderant in case of a metamorphic or metamafic rock in amphibolite grade or amphibolite facies. Now, cordierite, which is a hydrous magnesium iron silicate, it is very present in granulite grade or late amphibolite grids of metamorphism in a pelitic rock. The other mineral which is very characteristic in pelitic rocks is staurolite, which might be as a resultant from biotite, muscovite, garnet dehydration melting in presence of water, as well as zinc might play a very important role, which is should be a minor element in a rock. So appearance of the staurolite in a pelitic rock is also happens or also is there because of presence of aluminium. So kyanite, sillimanite, staurolite, cordierite are all signs of a metamorphism of a pelitic bulk or precursor, which we may find as paleozoom in a rock. Now, this is important because increasing grades of pressure temperature, obviously I am telling you regarding about facies. Now facies, what is that? Facies are the regions where a particular pressure temperature will be denoted by a set of minerals. The lowest grade of pressure or temperature that we have known about is known as prehnite pumpelite facies. Then there is a region which is known as green schist facies. Then the region of facies, it is known as amphibolite facies. In this region what we get is a blue schist facies of metamorphism, and here we get eclogitic facies of minerals. And after the amphibolite grade, the facies we know it is called the granulite grade or granulite facies. The next region what is there is UHT or ultra high temperature metamorphic terranes or facies of minerals, and this region is known as ultra high pressure, or this region is known as ultra high pressure region of minerals. In this domain, high temperature high pressure granulites or high pressure granulites are preponderant, and whether or when we try to analyze the structures or the textures of different types of minerals present in the slide or in the field, we try to analyze the minerals which we might find in different cases or instances. Like in case of a pelitic rock metamorphosed in a high grade granulite, we might try to find out some sillimanite, some cordierite. In case of a high pressure, we might try to find out some kyanite, or if we find some kyanite, then we might find out the facies of pressure was probably eclogitic or might be blue schist facies. In case of metamorphism of a mafic rock, what we see is that in mafic rocks we see the lowest grade, or in amphibolite grade we find out some of the amphiboles. And amphiboles, which are generally we find solutions of Schermack Schermackitic amphibole, or Schermack is rather, it is a vector which we might find out, as well as there is another vector in case of amphiboles that we might find out, it's called edenite, which are both substitutional vectors in amphiboles. Now this region you should check it that what type of a substitution it is, what is Schermackitic substitution, that is aluminium versus Si or magnesium. Try to check it out. What are the substitutions those are taking place? Like in case of edenite, what type of a substitution is taking place in lieu of sodium or something, or aluminium, or in terms of silica, and how the vectors are operating in the or during the changes of the pressure or temperature. As well as there are, in case of a mafic rock, what we find out, it is a mineral which is called glaucophen, or blue schist facies, and glaucophane is a very typical mineral which we find out in case of mafic blue schist facies metamorphic rocks. And here we find out some of the jadeite pyroxene. Jadeite pyroxene, which is NaLSi2O6. So obviously some of the sodium from pre-existing mineral might have transformed to jadeite in eclogitic facies, where the metamorphism was taking place, where another phase of mineral was not stable and the sodium entered into the structure of the jadeite. Try to find it out which could be the mineral. As well as in high-grade conditions, magnesium garnet, as well as like pyrope, it is very preponderant in case of mafic rocks. So minerals like omphacite, jadeite, amphibole, as well as garnet of typified mafic mineralogy are signs of facies of metamorphism in mafic rocks. So try to find them out, and this is a very short discussion, and try to find the materials in the Google Classroom that I have sent you, that what type of a transfer, whenever it is, and I have also sent you those links, those things in WhatsApp, I think a month or 2 months ago, before the examination obviously. So 2 or 2.5 months ago. It is just brush them up, and thank you.